Okay, hello. Welcome everyone to the November Potpourri.
On a project we like to call Searching for Stellar Streams with 10 million stars in the Milky Way. And I'll preface this with, I've been looking at this stuff for many months. So if you have any questions, feel free to ask at any point, and I'll try to answer them to the best of my ability. So yeah, let's begin. What are stellar streams and why are they interesting? So a stellar stream is formed when a globular cluster or a dwarf galaxy, these balls of stars, get tidally stripped by the Milky Way. And what this means is they're just gravitationally interacting with the Milky Way. They're orbiting it as they should. And this is a great simulation. Please.
There it goes. Max.
All right, perfect. So the green dots there are,
you want it? No,
it's
okay.
fine. It's fine.
Sorry.
All good. But the green points are the globular clusters in the dwarf galaxies. And as they orbit the Milky Way, some parts of the ball will experience slightly more gravity than the other side. So as it orbits, it gets slowly pulled apart until it becomes a literal stream of stars in the sky. So why are these cool? It's because they tell us about the formation history of the Milky Way. So it tells us about the accretion events that happened, all of the mass that's been absorbed, and also the mass distribution within the Milky Way. And in particular, what's really interesting is the fact that we can look for things like dark matter subhalos. Ooh, dark matter. This fancy little particle that like no one knows about. But our best model says that they should clump together the same way that globular clusters and dwarf galaxies clump together. And when a stellar stream hits it, it'll perturb it because gravity. That's all we're looking at. Please. Okay, there we go. So in a perfect world, we'd expect a stellar stream to be perfectly uniform. However, this is not the case. So the first perturbation that we look for is called an epicyclic overdensity. Super long name, but all this means is if a part of a stellar stream is slightly more dense than its neighbor, it's going to pull slightly more on the stellar stream that's less dense than the less dense part, and the less dense part will pull slightly less than the overdense part. And they cause these little spurs in the top left panel. They cause these little spurs in the stellar stream that we can look for. In addition, we can look for when these stellar streams interact with the bar of the Milky Way. So the Milky Way, we think, is a spiral galaxy with a little bar in the center. And when the stellar stream interacts with it, it's going to pull it out and stretch it really, really thin, as you can see in the top right plot. And finally, the last one is when a stellar stream interacts with a dark matter subhalo. It's much smaller perturbations, but it's really, really cool. And there's a lot of researchers right now in the field looking at when do these stellar streams interact with these dark matter subhalos? What are the masses that need to cause this kind of perturbation? How far away do they need to be? And how frequently do we find them in the Milky Way? All right, so the data I've been using so far is a new survey. So unlike Gaia, this is a new one that we're using. It's from the Dark Energy Spectroscopic Instrument survey, super long name. But it is the points in black, as you can see from this plot, and it covers the entire northern hemisphere. So it's really, really cool because it's a spectroscopic survey and it's gotten over 10 million stars. So a lot of data for me to work with and play around with. In addition to this, we're using 3 stellar stream catalogs, one from gal streams, which is the lines. They tell us the track or the path that these stellar streams follow. Streamfinder, the DR2 and the DR3 survey are even more interesting because for some of these stellar streams, they tell us the actual members, the stars that belong to these stellar streams from the Gaia catalog. So these are really useful when we make an initial guess or an initial assumption on these stellar streams, which will come in later. Ooh, cool transition. I love this one. But when you zoom in on a piece of the sky, if it wasn't colored in like I have here, it's really hard to tell the difference between a star that should be a part of a stellar stream versus one that's in the background or foreground. It's just all black dots. But when we look for these, what do we expect of stellar stream stars and their members? First of all, we look at their 6D kinematic space. Fancy word, but all it means is in 3D, it should look like a stellar stream, right? That's what we expect it to look like. But in addition to this, because they form together in the same place, have the same amount of time to interact with the Milky Way, and have interacted with the same things, we expect their 3D velocities to also be the same. So they should all follow the same orbit around the Milky Way as well. And because it's a spectroscopic survey, we have the metallicities of these stars, which is very simply the proportion of iron to hydrogen within these stars. So this is also another thing we expect because once again, they formed in globular clusters and dwarf galaxies. They formed with the same materials and have had the same amount of time to evolve. So we expect their metallicities to be somewhat the same as well. All right, to get into a little bit of the nitty-gritty, the first thing we have to look at is the fact that these stellar streams are observed from Earth, right? This is observation, what you guys all look great at. And you observe stars in RA and DEC coordinates, which is very intuitive, hopefully. But for a stellar stream, that doesn't make sense, because what if you have a stellar stream that you're observing from Earth that's projected along our line of sight? We can't really get much information from it because it no longer looks like a stream. So we apply a rotation to this RA and DEC to new coordinates called phi1 and phi2. And all this does is it takes the stellar stream and tries to align it perfectly along the x-axis and centers at 0, 0, 0. This is also really useful for our fitting later on. We'll get into that. But basically, this is our first coordinate transformation. In addition to this, we have to look at their velocities, since it doesn't make sense for us to look at a star and say, okay, what do their velocities look like from the sun? They don't care about us, unfortunately. They only care about the large gravitational field at the center of the Milky Way. So if you're looking from the center of the Milky Way, we have to look at how the stream interacts with that. So we convert from heliocentric velocities to galactocentric. Galactocentric's on the bottom, I will say that. So yeah, now with all this data, once again, I said we have 10 million stars. And if you're trying to fit for 10 million stars, you're going to find a lot of baloney and a lot of stuff that just doesn't make sense in a stellar stream. So we want to limit our search a little bit and just get rid of the members that we know for sure shouldn't be a part of the stellar stream. The simplest case is for phi2, so our y coordinates. We're doing a 2-degree cut in this case, and it basically says, okay, if you're a star on the opposite side of the Milky Way, you probably aren't a member of the stellar stream. So we can get rid of that data comfortably, knowing the fact that it might not be in there. This catalogs also give us a great initial guess at these initial metallicities for these stellar streams. So all we do is we put an upper limit on it. And same with the radial velocities. So if you're looking for galactocentric, I don't know if I can go to the last slide. Oh, perfect. But basically, if you look at the bottom plot, most of these stars and the stellar stream members belong below a radial velocity of -100. So there's not really a point to consider the stars above it because they shouldn't follow on the same track and orbit. One more thing we have to cut out for is distance. So these stellar stream members are generally much, much further away, from like 5 to like 20 to 30 kiloparsecs away from the Earth. And because our instruments are biased towards stars that are nearby, that are brighter and have larger parallaxes, we just want to cut out some of them and say, okay, there's a lot of foreground stars, and most of them aren't going to be a part of our stellar stream. So we're just going to ignore them. Finally, the last technical cut that we need to make is an isochrone. I don't know how familiar you are with a CMD, or color magnitude diagram, but basically an isochrone is a theoretical model for stars that if you know a star's age and its metallicity, you should be able to predict or know along what track in brightness and color space it should lie along. So we just cut around the stars given the initial guesses from before with a plus or minus of some color index, and we ignore the stars that aren't in it, as you can see in black. All right, now into the juicy stuff. What are we actually fitting for? So the plot on the right is quite intensive, so bear with me for a minute. But basically all it's showing is the different phase spaces along X. So at the top, you'll see X and Y are phi1 and phi2, which we've talked about before. This is what it would look like if you're just looking at the stream at its XY coordinate. The second grid shows you X in distance. So just flip it by 90 degrees and you're looking at the stream like that. And the last four are what we're fitting for. So the radial velocities, the metallicities, and the two proper motions. Proper motion is the velocities along X and Y, or RA and DEC in our case. You can see that most of these members, especially in the phase space, the last four, follow a parabolic fit. So when we sample our space and fit for these tracks, these paths that the stellar stream follows, we're looking for a parabolic fit. So we're going to have an A, a B, and a C. If you know from the quadratic formula, these are all very useful for understanding parabolas and where they intersect the x-axis. And if you remember, we just centered our stream at 0, 0 along the x-axis. So this is much easier for fitting than if you looked at it at like RA 200. Like what would the y-intercept be at that case? It's hard to understand. Another thing that we need to fit for that's really, really important is the fraction of stellar stream members to background members. We've already made a lot of cuts to this data, but say we have 100 stars that are left. Oh, sorry, I should mention that the stars that are left are the plots in black. The purple ones are ignored. So while there doesn't look like there's that many, in our code, it shows there's like at least 500 of these that are still unfit for. So the stream fraction tells us if we have, for example, 100 stars, we want to say that like 10% of these stars along the x-axis should be a stellar stream member. And this is something we have to fit for and understand, because if we have a really long stream, we want to assume that it's constant and the stream fraction is constant along it. This isn't always true, and I'll show you how we fix that later on. But for now, we're going to assume a constant stream fraction, which just says, if you look at stellar stream, we can say 10% of these members should be a part of the stellar stream. And we'll calculate membership probabilities later. All right, Markov chain Monte Carlo. This is what we're fitting. It's a really cool thing, and I'll play the simulation in the background. But all it says is, okay, we have some likelihood, we have some statistics knowledge. So if I start at some random step, and I take another step in some random direction at some length, it could be small, it could be big. Is this next step better or worse for modeling our data? In this simulation, if it's worse, it's shown as a red point. If it's better, it's green. And what happens is if we take this next step and it's worse, it doesn't model our data correctly in its space, we ignore it and we stay where we are. But if it's good, we go to that next step and try again. And we take another step, and we go on for thousands of steps. And you can assume that if you go to infinity, if you take infinite number of steps, you're eventually going to recreate these distributions at the bottom and on the left-hand side. And you're going to know to some degree, or like to really high degrees, where your data lies. To what standard deviation, how spread apart is it, and where exactly it's laying. So this is how we do it in 2D. But as you remember, we're fitting for 4 different things. Each need a parabolic fit. Each need its standard deviations. We have streams, like the fraction of stream, like we're fitting for at least 25 of these parameters. So if your mind is powerful enough, you can imagine 25 different phase spaces of these, and that's what we're trying to fit for. At least the computer is. I cannot imagine that. All right. The technical name is a truncated Gaussian mixture model. Basically, what this means is if you plot over all of our data, as you can see here in a histogram, you should be able to fit 2 Gaussians to it. One for the background, which is in orange, and one for the stellar stream, which is in blue. In this case, it's really obvious which one it is in VGSR, the top left panel. And we truncate this once again just to decrease the number of data that we need. So our likelihood function, our decision for whether or not we should take that next step, is based on a likelihood function saying if we take a star and we have its velocities, we have its proper motions, and we have its metallicity, should it belong to the Gaussian initial guess that we've sampled from or that we've made in our data? If it's a good step, we walk towards it. If not, we leave it in the past. It's very simple. We do this with Gaussians because Gaussians are easily added together and they're great, perfectly normalized. With our initial guess, we first take a SciPy optimization, which says, okay, look at our data. Where is the local maximum? How can we maximize the number of stars that are in this stream Gaussian versus the background? With this maximization, we then plug it into the MCMC. And the MCMC does this cool thing, does this random walks, takes 30 minutes to an hour. It's a lot of waiting. But once it does all of this, we know its standard deviations pretty well for these stellar streams, which is really important to understand their evolution over time. As a stream evolves over time, you can think of its metallicity. It starts at some very uniform, similar metallicity. But as it grows, some stars are going to go supernova, some aren't. Some are going to evolve faster than others. So we're going to have some standard deviation to all of this. So all right, let's get into my results. So the first stream that I looked at, which is really interesting, is Silgi. It has a really low metallicity, which is very strange because as these streams evolve over a long, long time, we expect them to also fuse heavier and heavier metals. But it's still really low metals. On the far right, you can see the plot that I showed you before, but now the purple points are the points that we've identified to be stellar stream members. And you can see it still follows along that parabolic line. If you focus on the plot on the left, though, the yellow stars are the high probable members, members that we think very strongly should belong to the stellar stream. In specific, the circular dots, not the diamonds, but the circle dots are ones that we think we found in our new data set that have never been identified before. And most of these lie on the far right-hand side of this track, indicating that this stellar stream is much, much longer than we previously expected. Another really interesting thing is C19. Once again, even lower metallicities, which is very strange and peculiar. On the left, the fit was much harder since we only had one star as an initial guess. So this is one that I'm still working on and developing over time. But if you look at the plot on the left, the blue stars are ones that were identified previously by the Gaia catalog and the Streamfinder group. And most of the stars lie in the top left. But in the bottom right, I don't know if you can see it or how close I can get. But in the bottom right, there's this one blue star that looks like an outlier. It looks like it doesn't belong. But with our method, we found that most of our high probable members fill in the gap between this outlier star and the rest of the stream. Once again, showing that whatever the other group did was good. And also this stream is much longer than we previously expected. And once again, it's still so strange because it has such a low metallicity, which is so peculiar. All right, so now what I've been working on these past couple of months is updating the code, basically saying, if we find a high probable member, how sure can we be that this star should be a member of the stream? So the first thing I've done is change these parabolic fits to spline fits. And all this means is instead of fitting for a quadratic formula, we have these little dots or nodes spread along equally along the x-axis. And for each phase, we say like, okay, the model's allowed to shift it up or down some given range. And from there, we fit a parabolic fit. It's really useful for really long streams because as you expect, long streams have more areas of like perturbations from different regions of the Milky Way. Some are interacting with the bar, some are interacting with the dark matter halo. So when you fit for splines, you're allowed to split it up into multiple sections and then fit for each individual section to get a better understanding of their standard deviations and their dispersions along X. Another thing I've been working on is varying the stream fraction. What's really interesting is the fact that some of these stellar streams still have their old globular clusters attached to them, which is the plot on the left. There's a large amount of stars that are still in their globular cluster, but have over time spread out slightly so that there are stream members. And if you assume a constant fraction, near the edges, you're going to overestimate the number of stars that should belong to the stream. But if you vary the stream fraction, if you allow it to change with X, you can account for this globular cluster, this higher density of stars, while still keeping the stream component, which is shown in orange over here. It's for the same stream. Oh, sorry. Hope everything's fine. But yeah, in conclusion, I've been using the DESI survey, which is a really cool new survey that should be out soon. Using a Bayesian mixture model, Gaussian mixture model, which says we're fitting two Gaussians to our data, one for the background and one for the stellar stream. I found new member stars that have filled in the tracks and extended the tracks of a lot of stellar streams. And this is cool because we get to understand more of what impacts our Milky Way and form a better picture of it as well. The next steps for this project are to fit for proper motions in these phi1 and phi2 spaces. I ignored the fact that we're fitting for proper motions in RA and DEC just because I hoped you would pick up on it. But basically, we want to see what the stream looks like in its point of view. We're also trying to include orbital integrations. And what this means is if we think a star should be a member of the stellar stream, we can fit an orbit to it around the Milky Way. And if one of these stars leaves the Milky Way or flies off to who knows where, then it shouldn't be a member of the stellar stream that we know has this defined path. So we're going to test with all this and calculate membership probabilities with this involved as well. We're also trying to test this model on all of the streams in the Northern Hemisphere. This is like over 50 of them, which can be quite tedious. And I'm working with a PhD student right now on this. But it's some really cool information because now we can do population level statistics on these stellar streams and understand how frequent are these dark matter subhalos in the Milky Way. So yeah, once again, this is all really cool work, and I hope to see this field explode even more in the future, just to understand where we live here in the Milky Way. Thanks, guys.
Red stars.
Okay. So the first part of the question is most of these do not have their globular clusters intact. In fact, most of these, we don't even know what their globular clusters were. Some of these we can date back, but most of them we can't. And for the other question about like what types of stars these stellar stream members are, they can be whatever stars they want. It's very spread.
Could some of these be captured galaxies as opposed to?
They could be
a
dwarf
body of stars?
galaxies.
Okay.
Definitely, they can be dwarf galaxies. Yeah. Any other questions? We have a mic person. That's easy for me. Oh yeah, that's great.
I have a pretty loud voice, but it's better to use the system. Are there any streams near our solar system? And what do you think would happen if a stream going one?
Yeah. So Silky itself is quite close to us. It's on the order of like 2 kiloparsecs. I don't know how familiar kiloparsecs are with you, but these stellar streams generally are much further away because, as you saw from the simulation, they're traveling quite fast around the Milky Way in comparison, and in different trajectories and different orbits as well. And sorry, what was the second part of the question?
What would happen if we?
It's just as if you were to fly around another star. Nothing's gonna happen. Like stars are quite spread apart. It's denser than the rest of the Milky Way. I can put it that way.
Yeah, this is very interesting. Thanks. So once you find all these streams and notice their direction and motion, can you then infer more information about the black hole at the center of the Milky Way or what's going on at the center of the Milky Way, assuming that they're all going around the center?
Yeah, so the main idea, another idea with these stellar streams is the fact that we can understand the Milky Way potential. So what that means is, yes, right now we're currently assuming just like, okay, if you had one black hole, like a large amount of mass at the center, that's fine with us. But there are a lot of other things in the Milky Way that perturb it. And we want to form an entire picture of the potential energy that the Milky Way has and how these affect the stellar streams and their orbits as well.
Did you encounter any errors, or are there any errors in the data that you found out due to gravitational lensing, considering they might have the same angular velocity or the same makeup because of the data that could have been captured? Or does it, I mean, does gravitational lensing or any other thing affect your data in any form or shape?
That's a question that's harder for me to answer because I'm not on the data processing side, but there's some really smart people working on this. And I think they have some way of accounting for gravitational lensing and things like that as well. I'm only focusing on the star portion of the data, but there's ones for like dwarf galaxies and etc.
2 questions. In your simulation, when you were the first slide, when you were showing the dwarf galaxies and globular clusters flowing around,
yes,
is Milky Way also losing material during that?
Oh, sorry. During the, like, not particularly from the stellar streams. Yeah.
So we're not getting dragged around.
No, not by these stellar streams are like on the scale of like hundreds of stars. Milky Way has like billions of stars. So I think we're fine for the most part.
Second question, I really enjoyed your steps that you went through. During the steps, did you like ever end up at like with data at the end that you like went through all the quality cuts and everything, but then when you got to the end, you were like, wait, this is wrong.
1000%.
Really?
Every single stream that I look at has something wrong with it. There's nothing ever perfect with it. These are cool ones. The ones I showed you today have really low metallicity. So if you looked at the plot with them in it, they specifically in their metallicity stream, they're quite like their own group. But for most of these, they have their velocity tracks hidden within the background. So when your code's trying to find it, it's like, okay, I could either fit for the entire background, or I could be like, there's nothing there. So most of the time, these are really hard to fit for.
So like you go back and like fix the math? Or...
Hours of like, this isn't working. Let me decrease this size. Let me increase this size. Let me ask my professor. And sometimes it's just like, ignore it. Move on and come back later.
Thank you.
Hi. Great presentation, first of all.
Thank you.
One impression which I really took away from your presentation was that everything is in motion and it's significantly which you can actually record. the one excuse which I often find myself making often on winter days is that stars are not going anywhere. They'll still be here even if when I'm 80 years old. But I'm wondering, after your presentation, how long do you actually have to observe a star to confidently predict its path of motion, which path is it following? Because human life is just not long enough to have enough data to have a confident enough path for it. I'm just wondering about it. How long do you actually have to observe a star to get understand its orbit
Yeah.
around Milky Way?
So they look like they're moving slowly if you're looking at it from the Milky Way's point of view. But for us, we can see, especially in the proper motions, which is like the X and Y, if you just look up in the sky, you can see it move ever so slightly. And this is sometimes over, this can be over like years, multiple years, but all you need is some shift in its proper motion or its position. And from there, we can infer some movement of it with obviously errors and uncertainties, which I didn't account for. Well, we accounted for it in the data, but I haven't included it in this talk. And for radial velocities, we have really cool ways of searching for it, specifically spectroscopy. And you can see, I don't know how familiar you are with like blue shift, red shift. So when an ambulance drives by, you hear like a different sound wave. Like that. Maybe moving a bit faster, but same idea. But basically on either sides of this spectroscopy, you can see some red shift, blue shift. And from there, infer how far away and how quickly they are moving away from. All right. Thank you guys.
Hello, everyone. My name is Alyssa. I'm a fourth year here at UTM, and I do my research downtown with a postdoc, and today I'm going to tell you a bit about it. This title has a lot of acronyms, but I'll just say it really quickly. Very long baseline interferometry with the Algonquin radio telescope and the CHIME telescope to localize fast radio bursts, and I'll get into the details of all of that and what CHIME stands for later. So I'm gonna tell you guys a bit about what fast radio bursts are. I'm not sure how familiar you are with fast radio bursts. I know that there's like a lot of almost like mystery surrounding fast radio bursts, and there's a lot of articles, but I'll just give a little bit of a background so everyone's up to speed. Then I'll talk about how FRBs get localized, so like how we determine exactly where they're coming from. And then I will talk about contributing to fast radio burst science with the Algonquin Radio Observatory, which is an observatory that's about 6 hours from here at Algonquin Park. So first, what are fast radio bursts? Before I talk about what fast radio bursts are, I wanted to give a background on pulsars, just so that it's very clear, and also pulsars are very important to understand when talking about fast radio bursts. So this may be a bit of a review for a lot of you, but pulsars are a class of neutron stars, and neutron stars are the result of a massive star that undergoes explosion and then it collapses, but it's not quite massive enough to become a black hole, so you get a neutron star instead. And one of the coolest features about neutron stars, one thing is they're very small, and two is because they're very small and they were once really huge, they rotate extremely fast, like so fast. And so what you get is a really interesting phenomenon in the case of pulsars. So you have this magnetic field that surrounds it, and this causes radio jets to be emitted from the magnetic poles. The exact origin of jets from pulsars isn't fully understood, just like the exact mechanism of jets from AGN isn't fully understood. It's a whole other thing, but the point is there are radio jets there. And so when this thing is pulsing, it's turning, this beam of radiation is kind of, if it's in our line of sight, we'll be able to see it every pulse period, every time that this neutron star rotates. I believe radio pulsars were discovered somewhere in, I don't know, like 1960s, I'm not entirely sure, but they're very interesting and they're very useful. And as we'll see later, they're related to this more mysterious object called a fast radio burst. So I just wanted to talk about a little bit of that second plot there, which is showing what is called a dispersion sweep, because that's also important for FRBs. So basically, this is a plot of, on the bottom, it's time, and then on the y-axis, it's frequency. And you can see that it does like this. and we call it a dispersion sweep. And the reason that that happens is because at lower frequencies, the radio emission interacts more with like the intervening matter between the source and us, which causes it to get like dispersed and it arrives later. And so in frequency, there's this sweeping pattern. And so that's very characteristic of kind of radio sources that we see. Okay, so now that we have a little bit of a background on pulsars, let's talk about the first fast radio burst that was discovered. It was discovered in 2007, and as you can see, there's a dispersion sweep. And so the difference between this and an average pulsar is that it was a lot more dispersed. This dispersion, when measured, there was a very high dispersion measure, something that could not be explained by this object being in our galaxy. Also, it didn't repeat, which means that it's not a pulsar, because pulsars, they pulse all the time, they repeat. So that was another very mysterious thing about this burst of radio energy that we concluded to have extragalactic origins. And also it's extremely energetic. So it's exciting because this could be some sort of high energy explosion that is very interesting, and we could use like these radio bursts to probe physics. And so also some people thought they were aliens. Some people probably still think that, so that's why I put that. I mean, maybe, I don't know. I'll talk a little later about how there's probably many mechanisms for FRBs, so maybe one of them is aliens, I don't know. Anyways, okay, so now I'll talk about CHIME. So in 2017, before CHIME was made operational, there were only 50 FRBs roughly discovered. Now there are thousands of FRBs. So CHIME, the Canadian Hydrogen Intensity Mapping Experiment, is this telescope that was built for cosmology. And then they switched it on and it was like FRBs every day. And it was pretty crazy because up until then, there hadn't been that many FRBs discovered. And so it wasn't expected, but CHIME became this powerhouse for finding these radio transients. So yeah. And so now it's been 17 years since the first fast radio burst was discovered. This is not an exhaustive list about everything that we've learned about FRBs, but some important things. One thing is that there is an FRB-like burst that was localized to a magnetar actually in our host galaxy. And so magnetars, which are also neutron stars, but they have much stronger magnetic fields than a pulsar or just an average neutron star. It was localized to a magnetar, so that's one potential explanation for FRB emissions, but it's not something that we can be sure of, and there are also reasons to think that not all FRBs come from magnetars based on where they're found in, where exactly they're found in their host galaxies. And so it could be different mechanisms causing FRBs. I was actually talking to kind of an FRB expert, Jason Hessels, once, and he said, it's not necessarily that we discovered a new event and we're trying to understand what it is, but it could actually be that we started building instruments that can detect radio transients like this. And now there's a bunch of different things that could be causing them. So that's something that's really exciting about FRBs. And in order to really understand these transients, we have to localize them. We have to know where they're coming from because that tells us a lot about their origins. That's how they were able to find out that this one was coming from a magnetar. And then if they're further away, if they're extragalactic, which a lot of them are, that's how you can find out like where in what galaxy are they located in? What does that tell us about them? Where are they located inside their galaxy? So yeah. Also, some FRBs repeat. I think about 10% of FRBs repeat, which was found a bit more recently. And that's another thing. Why do some repeat? Why do some not repeat? There's a lot of open questions in FRB science right now. So now I'm going to talk about localizing these things because that's one of the biggest goals in the field. So we need something called very long baseline interferometry. So CHIME on its own, it detects the radio burst. It tells us where it is to some precision, but it's not good enough to actually tell us a lot of the things that we want to know about these radio transients. So there's a little diagram there, and it's kind of showing the big white circle is what CHIME can do on its own. And it's not very precise. It's just like a kind of quick thing to explain. And then the blue one is VLBI localization. So using very long baseline interferometry, and you can localize the FRB to its host galaxy. And then the pink thing is potentially what you could get if you're using very long baseline interferometry and very precise atomic clocks. And I'll talk about why atomic clocks are important in a second. And I should note that this whole thing here depends on how far the FRB is. Like if it was closer, then this would be potentially, again, localizing it to a source, which could be very interesting. But it's just to say that VLBI gets you much better precision than just using a single telescope. So I'll quickly talk a little bit about how VLBI works. Essentially, you have two radio telescopes that are separated by some long baseline. The longer the baseline, the better your precision is. And the fact that they are separated causes this, delay, this time delay that you can measure in your signals. And that delay tells you where the source is coming from. The reality of VLBI is that there's a lot of other things other than that geometric delay that contains where the source is. There's also the clocks, which is why we need atomic clocks that are very good. There's other things like the ionosphere of the Earth. So there are a lot of things that can affect how precisely we can do these localizations of fast radio bursts. And so a big thing in this field is trying to see how well we can do VLBI and do it really, really precisely. So this brings me to CHIME FRB outriggers. So right now there's a project in kind of its commissioning / beginning science phase called CHIME FRB outriggers, and it's smaller CHIME-like telescopes. One's in California, one's in BC. I forget. Oh, the other one's at Green Bank. And so they're being built to do VLBI with CHIME so that we can localize CHIME's FRBs to better precision and try to use that to tell us about the origins of these objects. So that was a bit of a background on the current state of the field of FRB localizations. And now I'll tell you guys a bit about how we can contribute to FRB science using the Algonquin Radio Observatory, which is what my project in the summer and continuing throughout this year is about. So how can ARO help? There's this thing called a CHIME side lobe FRB. So CHIME is like this parabolic dish, and it's looking up at like the meridian like this. And then when we have an event coming from up there, we call it a main lobe event because this is like the main beam of CHIME. But if you had an event coming from over here, then it's not really in the main beam of CHIME, it's in the side beam. And so in order to see an event in the side lobe of CHIME is what we call it, it has to be super, super bright, and which indicates that it would be potentially close to us. And so that's what a side lobe FRB is. And the CHIME FRB outriggers project is not made for localizing side lobe FRBs. It's made for the main lobe FRBs because there's a lot of those and you can do statistical analysis. But side lobe FRBs are also interesting because they're very bright, which means that they're probably close to us. So localizing them with VLBI precision could mean localizing them to like a source. And so that's where this instrument that I'm showing here called the log periodic dipole array, sorry, I didn't put the abbreviation up there, but it's called log periodic dipole array. That's where that instrument comes in. And you can see just how small and dinky this little instrument is because that's me and some of the people I work with standing next to it. It's very small compared to CHIME, which is like huge. But the idea is it has a super wide field of view, like really, really wide field of view with the way that it's designed, just low sensitivity. But the way that VLBI works is you do it with correlating signals. So if even there's a little bit of signal, then we could correlate that with CHIME and potentially localize these side lobe events. These types of antennas are very cheap, and there's a lot of upcoming projects involving building giant like arrays to do FRB localizations. So it'll be very interesting to see if these antennas can successfully do VLBI. So there's a couple steps to do fast radio burst localizations with this instrument. The first one is validating the clock stability of our system. And there it says finish validation because I already started the validation. I'll talk about that a little bit later. But essentially, ARO got a new clock. And and we need to test that its clock in combination with Chime's clock is stable enough to do VLBI, because you have these two atomic clocks, and if if something is wrong with one of them, if this system just has a lot of errors over time, that's not good, because time equals precision. Like your timing precision equals your localization precision. So once we are fully confident in our clock system and our timing and everything, then I want to start localizing sources with the log periodic dipole array. I should note there's another one of those LPDAs in Hawaii. It's a little bit earlier on in its commissioning phase right now, but the end goal would be to do localizations with that, because when you localize with two telescopes, you get one axis or like one dimension, and then you need another dimension to do it full localization and get RA and DEC of whatever your source is. And then finally, after doing that test, because we want to make sure that we can even localize anything. So the second step would be a known source like the crab pulsar. And then the final step would be to hope that we observed an FRB recently enough when the LPDA was in operation, and hopefully that's also at Chime, and then try to localize it. So just to talk a little bit about how this is done, and in the part of my project that I'm showing you, I use the big dish at arrow because it all runs on the same clock system. So when we're trying to test the clocks, we use the telescopes that we already know work. So basically what you do is you correlate the signals, which basically means multiplying them by each other. And then you see where the correlation is maximum. You see where like you get your biggest peak, and then that tells you where like what the delay is between the two systems. And so if you're interested in what the source is, then that would tell you where the source is. But if you're trying to make sure your timing stability is good, then what you do is you get rid of the geometric discrepancy between the two stations, and then you do the same process, and then you can get like timing residuals. And this is talking just a little bit more about that getting delays. So what I just described is lag correlation, seeing where the correlation is maximum. There's also a method called fringe fitting, which is taking the lag correlation as almost a prior and doing a bit of a grid search over delay and ionosphere, and or what says DM index, that's the ionosphere. So like the delay that is caused by like the ionosphere of the Earth has a different dependence on frequency than the other delay, so you can fit for it and get rid of it. So that's what the fringe fitting is there, and that's kind of what I'll show you in the next plot. But just to be clear, that's the ionosphere there that's like messing up the radio waves and making everything difficult. That's what I'm talking about when I say the DM index. So that's just a little bit about the technical details of how we extract the delays to track them over time, because ultimately we want to see that our timing residuals are stable over time. And so these are some results from looking at pulsars. Oh, I guess one of them didn't show up. Sorry about that, but it's pretty much the same thing as the other pulsar. At least one of them showed up. So here, this is showing, so you look at a pulsar and you correlate it over and over again with chime. So we have arrow and chime. And then you extract this timing delay. And you can see that, and this is over roughly 5 minutes. So you can see the kind of the variance on this line is very little, which corresponds to a very good localization precision for your fast radio burst. So that would be great. And the reason you need it to be stable over time is because when you localize something, you need to calibrate it to something that you know where it is. So if you have a calibrator 5 minutes before, you need to know that your timing isn't drifting or isn't getting like messed up in between that. Otherwise, you're going to attribute that to where the source is when it's actually just a timing error. And so you will notice that there's some drifting here. It goes like this a little bit, which isn't great. This is most likely to us not knowing the coordinates of our telescopes perfectly, which introduces this drifting. So this is most likely not a clock issue, but this is something that I calculated that over 5 minutes, it would cause milliarc second like errors in your localization, which is still good for localizing FRBs, but we can do better and we want to do better. So we want to be able to fit for and remove this drift. And if you could see the other pulsar, I would be able to tell you that it has the same slope, which means that it is likely a systematic thing due to the baseline, and we can fit for it and remove it. And then we'll have very good precision, like nanosecond timing precision, which is great for localizing FRBs. And so currently I'm working on doing that process, the same one here, but for longer timescales, so say over a week, because it's possible that we have a calibrator well, we probably would have a calibrator a couple hours away, but just to make sure that the timing's all good, I want to do the same thing over about a week. And that would be using the crab pulsar, and there's like a 10-meter dish at arrow. And so this is just, I recently beamformed this, which is why I put it up. Beamforming is like a chime, because it's like the cylindrical dish. In order to point it at something, you have to like add gains to the different inputs. So I recently beamformed this crab pulse, which is, so I just figured I'd show it because I just did it and I was excited about it. But yeah, so I also have this pulse and arrow data. So I want to do that correlation, extract the delay, and then do the same thing for like a bunch of pulses over a week, and then just see if the timing is behaving how we expect and see if we can fit for that drift. And then after I'm done with that, then I can start getting to the log periodic dipole array and trying to localize sources with that, and then see if we have any FRB dumps and potentially do an FRB localization. That's all. Thank you.
You mentioned earlier that FRBs can repeat. So how do you differentiate between an FRB that repeats and a pulsar?
So I would say one thing is that most FRBs are extragalactic, which means that the DM would be different. Like the DM should be larger, because a regular pulsar, if it was in another galaxy, it wouldn't be highly energetic enough to see it. And so if it's extragalactic, then that's how you would differentiate. If it was in the Milky Way, then you would probably, again, use the kind of the energy, because we don't expect pulsars to be as energetic as fast radio bursts. And I think that's how they would differentiate. But that's a good question, because I mean, they localize it to a magnetar, which is similar to a pulsar, but they don't know exactly what the emission mechanism was. So it's a little bit fuzzy, but that's what I would guess they do. Yep.
Is there any correlation between fast radio bursts and the gamma ray bursts that have been detected?
That's a great question. So I'm not entirely sure, but I do know that there's a lot of follow-ups done, or there's a goal to do follow-ups, fast radio bursts with like multi-wavelength studies. And so potentially, but I have not personally heard or read anything about correlation between the two, but there could be. And like I said, there could be a lot of different reasons for fast radio bursts. So it's possible that some of them do overlap with GRBs.
I got one question. We did have a talk by one of the fellows that was setting up Chime. Was it Agnew? Not sure. Anyway.
Yeah, we had,
we had a talk. And it was pre-COVID. And one of the problems they were running into was they were using a lot of graphics cards to do the processing. I'm assuming you must use similar backend hardware to do the signal analysis. Do you have but you have little rinky-dink antennas, but you must have some pretty fair computer hardware behind the scenes.
Yeah. So you mean that for the LPDA?
Yeah.
Yeah. So there's a lot of, like you said, stuff behind the scenes. I actually got to visit. There's a lot of, there's this thing that they use called an X engine that does like the correlation. I don't know that much about the X engine, but it's kind of like the one that's used for the LPDA would be like a smaller version, like a smaller scale version of what is done for Chime, because there is multiple inputs, but it's this like very, very powerful machine that takes all the inputs and it has to correlate each input with every other input. And then it spits out like some raw data, and then that raw data takes a lot of power to process. So yeah, did that answer your question?
Hi, my name is Dalisay. I'm a member since summer 2019. So 2024 is really a great year for us. For me, as you can see, these are the photos that I took this year. So if it is with so many great things happen, how much more with the Northern Lights? Okay, so I'm gonna share so my talk is very relaxing, not so much math. We're just gonna enjoy the pictures. So I'm gonna share the experience that I had this year in seeing the aurora, not once, not twice, but 5 times this year. Okay. So during the May 10, probably some of you took the pictures because it's also a very major geomagnetic storm. So luckily I was in the flight going to Lisbon that time. So from Montreal, from Montreal to there, it's there. On top of the Atlantic Ocean, these are the views that I was able to take. I only have a Google Pixel, and it's a challenge to take pictures. But as you can see, it's so purplish here. But at the naked eye, it's just white. It's not as colorful as this. As we all know, the camera take more lights than the naked eye. So, but yeah, in the pictures, it's very beautiful. So this is one also of that from that night. And like I said, from the moment we took up from Montreal up to the almost the day is coming, sunrise, still you can see there's that northern lights and there's the glow of the rising sun. So from that May, I had that. And then on July 25, my trip to Edmonton, I also when I look at the Up in the Space Weather Dive, I was able to see that there's like a northern lights. And then just in Ontario, this is Lake Superior. So I was able to see the northern lights. So this is it's hard to take pictures. So I see, as you can see, this is the one that's not edited. Then I used the magic eraser in Google to remove some of the flares. And here, that the location that I showed earlier, that is the one of the, I think in Thunder Bay. And so the challenge in here, so I was able to see the northern lights in Ontario. Going to Alberta during July, the day is very long. So by the time I was in Alberta, it's bright, it's still bright. So I was not able to see more of the northern lights there. Going back on that trip on August 6th, again, there's the northern lights, but I can see this on my naked eye very bright when I cover, like put something on my head. This is very, very bright, but it's I don't know. I was not able to take a good picture, and and we're traveling farther away, so I was not able to take more. And then of course it's red eye flight. I sleep, and then around in Manitoba, this is the picture that I was able to take. So that was in August. And September 25. Yeah, this is one of the most beautiful aurora lights that I see. Like I know I sent this through the email, and I remember Leslie asking if the swirls that I saw was really visible to the naked eye. Also the colors I was able to see. It's not just white like I mentioned in the one to going to the Lisbon. This one is kind of like this color, like greenish and little bit of yellow. So this is already in Alberta area. This one too is from that flight. This one is from Saskatchewan area. So it's just starting to glow in that time. And then when I reach Alberta, so this is the one. So this is the one that I cropped, and this is the original one. So as you can see, that's the challenge in taking pictures through the airplane, the lights, the cabin light. So I suggest that if you have something like a black cloth or a blanket, that would be a good one. The thing that I blacking this and that one is the neck pillow that I have, that this time is color black, and you can transform it into like just a pillow. So I was able to use that as a cover. So next time, I'll make sure that I'll bring a black blanket so that I'll be able to see, capture more if there's something. So that was in September 25. So coming back is, so this is a few hours before my flight coming back to Toronto. That was in October 6, 2024. So this is the first time that I really saw the pink, the color through naked eye. It's not just white. It's not just, this is really, it's not as bright as this one, but you can notice the color, the red color in it. It was very beautiful that night because I was in my friend's place. It's an acreage, so it's also a dark place. So it's really nice. So few hours before the flight, I don't want to leave, but I need to go back here. So in the plane, this is what I saw. During that night, October 6th. So this part is already in Manitoba area. And with the Google, if you have like astrophotography, there is a astrophotography setting, and then it will, so it's for 4 minutes taking photo, and it will create a 1 second time lapse, which is this one. So and then this is the other picture from that night. So exactly October 6, 2024, 3 years after the first time I saw the Northern Lights to the plane, October 6, 2021. So it's really, yeah, so I'm so lucky to have to see the Northern Lights 6 times on the plane. And speaking of Northern Lights, I know it's the topic is in the plane. I just want to share some of the pictures from the October 10th here in Ontario. So this one is in Jack Darling. So it's very bright, but still we're able to see the color. When it peaked at around 10 o'clock, this is the photo as well. The plane is still hunting us, so it's photobomb the pictures. So yeah, this is from there, and yeah. So yeah, that's all.
Dalisay, any questions for Dalisay?
Yeah, did you get any of those in the after shot?
Yeah. Also, Dalisay, in some of your pictures, you captured the Air Canada rondelle. And if you send that into Air Canada, maybe they give you a business class flight somewhere because they give you a blanket that you could put on.
By the way, one thing, always make sure that you sit on the north facing side.
Yes. Or ask the pilot to turn around.